Hi, welcome to SACE Mathematical Methods. So I will begin with what I call the chapter 0, whereby in this particular chapter I will introduce the notations and so on. So this is not officially inside the SACE Mathematical Methods syllabus, but it is very helpful for you to solve the questions in the exams. So these are, you can say, the prerequisites that you need to know before you enter this particular course. So I will call this the chapter 0. So we will introduce some notations. So let's begin with the first definition that we have. What is a set? So a set is basically a group of mathematical objects with the same property. So a set is a group of mathematical objects with the same property. So what are the examples of sets? For example, if you say the set of all colors. So the notation for writing a set, basically, there are a few different notations, but if you want to list down all the elements, you can do like this. So you enclose the curly braces. So the set of all colors, you can start with, for example, blue, green, yellow, and so on and so forth. So this is one way for you to write the sets. Another example would be like, for example, the set of all integers. Then you can list down all the set of integers and you know that this is infinite. So you can start with 0, plus or minus 1, plus or minus 2, and so on. So this is one way for you to write the sets. So from this particular example, if let's say you have some element x of a set, capital X. So how do you write this? You can write this as this particular symbol, the small x is an element of capital X. So looking at the examples from above, you can say that, for example, minus 1 is inside the set of all integers. So later on, we'll give a special name for that particular set. So what are the important examples of set? So this will be useful when you go through the mathematical method courses. So before this, we define the set of all integers as the name integers. Actually, you have a name for it, or you have a symbol for it. It is the somewhat weird symbol of Z, and this is by definition the set of all integers. So this is another way of writing down the definition of set. So basically you define what is a set, then you don't need to list down all the possible elements. The second very important example would be this weird symbol of R, and this is the set of all real numbers. So the third and the fourth example is somewhat ambiguous because in different books you can find different types of definition. So the definition that you definitely won't get confused will be this particular notation. If you see the weird R letter with a plus on top and then with a star at the bottom, so this set is equivalent to this set, and by definition this will be all x in the set of all real numbers such that x is greater than 0. So what does it mean by this particular definition? So this is basically the set of all positive real number. So why do I say that sometimes the notation can be confusing? Because in certain books, this particular notation can be denoted by this particular set. So if you want to include 0, what should you do? You just write R plus. So R plus can be also written as this particular symbol, and as you can guess, this is basically all x in R such that x is greater or equals to 0. So by definition, this is the set of all positive real numbers, and this time you need to including 0. So this notation in different books, they mean different things. So some books just say that this is the set of all positive real numbers, which does not include 0. And some books say that it includes 0. So in order to avoid confusion, it is better you denote the one with the star at the bottom or this particular notation as the set of all positive real numbers. And you just keep this particular R plus as the set of all positive real numbers including 0. Then you won't get confused. So those are the important examples of sets. So after we know what is set, the next thing that we need to know is the set operations. There are only two particular set operations that we need to know. The first one is the union. So the union can be written as x union y. So x and y are two sets. So what is the definition of the union operation? The union basically is a set of all things that are elements of x or y or both. So one example would be, if let's say your x is defined to be having the elements a, b, and c, your y is defined to have the elements of c, d, and e. So x union y in this particular case will be a, b, c, D, and E. So for union, X union Y, Y union X is the same thing. It gives you the same set. So those are the same thing. The second operations that you would need is the set difference. So the notation will be X, this particular slash Y. So what is the definition of set difference? This is the set of all things that belong to X but not Y. So this is important because now the order matters. So if you look at one example, so let X to be having ABC, and Y having B, D, E, and F. So the set difference of these two, if you have X set difference of Y, you would get A and C. A and C belongs to X, B belongs to X and Y, so you need to deduct B out. So X set difference of Y will be A and C. If you study Y set difference of X, you will get the opposite results, which is D, E, and F. So in this particular case, they don't mean the same set. Okay, so after we know these two set operations, next thing that we need to learn is the idea of functions and relations. So the first thing, what are relations? A relation is an assignment of elements in one set to elements in another set. So there are 4 types of relations. So the first one is the one-to-one relation. So one-to-one basically means you have, so let's say you have this. So from one set to another set, you basically map, let's say something like this. Each of the element from set X, so let's say this is set X, this is set Y. Each of the element in set X is mapped to one element in set Y. So that will be one-to-one. The second one will be many-to-one. So let's say you have the same setup A, B, C, D, E, F. So by definition, you can have something like this. Sorry. So A and B map to E. So this is an example of many to one. So the third type of relations will be one to many. So the same setup. This is set X, this is set Y. One to many means one of the element in set X can be mapped to multiple elements in set Y. Like this. So this will be one to many. So the last one, which is D, will be called many to many. So then you already know by the name, many to many basically means a combination of many to one and one to many. So let's say you have many to one, sorry. So this would be many to one, and then you have one to many. So C is one to many. So this would be one example of many to many. So among all these four relations, only one to one and many to one. So these two relations are functions. Okay. So now let's look at the definition of a function. So we have covered what is a relation. So now let's look at the definition of function. A function from a set X to a set Y is an assignment of an element so this element is Y to each element of X. So usually the notation we write something like this. F is a function that maps X as a set to Y. Or if let's say X belongs to the set X, Y belongs to the set Y, then you can also write x maps to the element y. So these are the two ways that we can write a function. Usually in exercises, what we would write is y equals to f of x. So this is what we would usually write. So now you can see the idea of function. Let's say this is set x, and then you have set y. So all these elements in set x is being mapped to a smaller subset in y. So from the definition above, f maps from x to y, right? So in this particular case, we can call x as our domain, y we can call is codomain, and let's say this smaller subset is fx, and fx will be called the range. Furthermore, if let's say you have some element smaller x, here is some element which is the smaller y. So this will be called the object of your function, and y in the set y, or specifically speaking your f of x, is called the image of f. So these are all the terminologies that you need to know. So the next thing, we need to study how to write intervals before we carry on to the idea of I would like to introduce what we call as the vertical line test. So the idea of vertical line test is to test whether or not your function is a function, or the curve is a function. So the idea is that if all the vertical lines intersect the curve of a function. So at this point, let's not call it a function. If all vertical lines intersect a curve, because before we perform the test, we wouldn't know whether the curve is a function or not. So let's not call the curve a function. So if all vertical lines intersect the curve at most once, then the curve y equals to fx is a function. So the famous example would be like this. Let's say you have a circle centered at 0. So if you draw a vertical line over here, let's use red lines. So obviously this does not intersect anything. So as you move closer to the circle, so at this particular point, the second line, basically you find that it only intersects at one point. But at some vertical lines, you will intercept this at 2 points. Okay, so this means that a circle actually fails your vertical line test. So a circle is not a function. So in other words, your vertical line test tests whether or not your function is one to many or many to many. So in this particular case, basically speaking, your circle is a many to many function. So how can we remedy this circle so that it becomes a function? If let's say you have something like this, a half circle, then at any vertical lines, you basically only intercepts the circle, the half circle at only one point, for example over here or over here. So then this is a function. So basically this is a many to one function. For the horizontal line test, I will introduce it when we reach to the idea of inverse function. So right now, remember that the vertical line test tests whether or not your curve is one to many or many to many. So your vertical line test tests C and D over here. If it only intersects at one point, then it is either A or B. And basically that particular curve becomes a function. So now let's introduce the idea of writing the interval first, because that will be important when we study inverse function. So the idea of interval is quite simple. You just need to know how to write closed intervals and open intervals. So let's say you have a number line over here and you want to include the endpoints. Let's say this is 0, minus 1, minus 2, minus 3, 1, 2, 3. So let's say you want to include the endpoints. Let's not draw on the number line. So if you have this kind of image, This basically means you include the endpoints. So let's say this is x. So this is what we call as the closed interval. A similar way to write is using the square bracket, -2, 1. So if you have another number line, -3, -2, -1, 0, 1, 2, and 3. So now you have 2 open circles, for example. So this particular interval will be -2, does not include your endpoints. So you can write something like this. And this particular open interval is written as your normal bracket. So this is what we call as the open interval. Of course, you can have mixed interval. So let's say this is open. And this is closed. So you write something like this. And this is similar to -2, 1. So this will be a mixed interval. You mix with open and close. So previously from the diagram wise, we say that this capital X is called a domain. Codomain will be the whole Y, and the range is the ones that maps from your domain through the function. So if you want a proper definition, domain of a function is the set of inputs accepted by the function. So the range of the function is the set of outputs given by the function because of the domain. So one of the very important skill is to identify the domain and the range of a given function or a given curve. So for example, let's say we want to identify the domain and range of the following. So for the first one, we have something like this. All the points such that y is x squared. So now the idea of the interval notation will be very helpful because it helps us to define the set properly. But in this case, basically this is a quadratic equation, so the domain will be the set of all R. So sometimes you can write something like this. So the range will be, so this you need to be careful because basically this is a U-shaped graph like this. So this would be R plus. So based on our definition, this will be R plus, including 0. But of course, you can also write something like this, including 0, and you cannot include infinity. That's why you need to put the open bracket at the end. So the second example would be this. Y equals to 2x minus 1. And this time I already specified the domain for you. It is from -1 to 2. So in this case, you don't need to write down the domain. The domain is already given. So what you need to do is to find the range. So if you plot the graph, you start from -1. So let's say this is -1. So you substitute -1 inside, you get -3. So this is -3, for example. And then you end at 2. And at x equals to 2, your y is basically 3. So this is your line. So you just connect back. So you can see that the range y would be from -3 to 3. So that will be your range. So the last example will be this. Square root of x minus 6. Find the domain and the range. So in this case, you need to look at the function itself. So square root of a number is not defined when it is negative. So the smallest x will be starting from 6 onwards. So x has to be starting from 6 and you can go to infinity. So now look at the range. The range will be when x equals to 6, basically your f of x is 0. And then as you increase your x, basically your y can go to infinity as well. So your y will be starting from 0 to infinity, or you can write the above. So we will end here. That's all for today.